Greetings, this is Mr. Garwood with our continuing series on Calculus 2nd edition by Briggs, Cochran, and Gillette. This video is going to focus on how to deal with points of discontinuity in rational functions. And so the example I'm going to work with for all of this is we're going to be looking at f of x equals x squared minus 4x plus 3 as the numerator and x squared minus 1 as the denominator. I have done a quick sketch of this with pen and paper, and I want to notice that we're going to be looking at 2 points. We're going to be looking at the limit as x goes to -1, and we're going to be looking at the limit as x goes to +1. And I've selected these 2 points very intentionally. And before I get into actually evaluating the limit, I want to look at why I picked these 2 points. First of all, if we look at the value of -1, if I plug in -1, -1 squared is 1, 1 minus 1 is 0, and so I have a divide by 0 error here. And what I want you to notice is at -1, we have a vertical asymptote, which I have drawn in red slashed line. And we're going to look at this and talk about why is this a vertical asymptote. Whereas at 1, again, if I plug in 1, I'm going to get 1 squared, which is 1 minus 1. It's also 0, but here I have an open dot with the function moving in around it. And so we're going to look at why that occurs in this video. I think the best way to explain why this occurs is for us to start by factoring this function in numerator and denominator. So I'm going to look at f of x equals, and now here, going back to our wonderful factoring from algebra in high school, I'm going to have x minus 3 times x minus 1, because -3 and -1 multiply to 3, and -3 and -1 add to -4. And the denominator is one of those special cases where I have the difference of 2 squares. So I've got the square root of x squared, which is x, square root of 1, which is 1, and I've got plus or minus. Now here's what I want us to notice. These 2 points that I'm concerned with occur because if I plug in +1, this gives me 0, and 0 times 0, anything is 0. And if I plug in -1, I equally get 0 on the bottom. So the big problem here is that I'm dividing by 0, and that's breaking stuff. That's bad math. So what I'm hoping you notice here is, hey look, I've got an x minus 1 on top and an x minus 1 on bottom, and those things are going to cancel. So I can say that f of x is the same. If I cancel the x minus 1s, I can say that f of x is exactly the same as x minus 3 over x plus 1 with one rule: if x is not equal to 1. And the reason for that is I can actually plug in 1 into this. I'm not breaking any divide by 0 problems if I plug in 1 to this, but I do in the original function, and that's creating our dilemma here. So let's start by looking at the limit I'm going to start by looking at the limit as x goes to -1 of f of x. Now, I do not have a clear-cut way of doing this. So to evaluate this, what I'm first going to have to do is I'm going to evaluate the limit from the left and from the right. And on this one, I'm actually going to do it just by looking at the graph. So if I look at the limit as x goes to -1 from the left, so I'm coming over here from the left, I'm increasing, and I'm blowing up to infinity. And if I look at it as -1 from the right, this one is going to -infinity because it's blowing up and going down. That one's pretty straightforward, I am hoping. Now, here's where things get interesting. If I instead want to talk about the limit as f of x, the limit as x goes to 1. So if I'm looking at the limit as x goes to 1 of f of x, once again I'm going to start by looking at this by going from the left to the right. So the limit x goes to 1 from the left, and the limit x goes to 1 from the right. Let's start by looking at these graphically. So as I'm coming from the left, I'm increasing, and it looks like I'm getting really close to -1. So graphically, I would say -1 for it. And then from the right, coming down, once again, it looks like I'm approaching -1. And this goes back to what we were looking at in section 2.3, where just because the function value doesn't exist or is different from where the limits are converging, notice here, this function is fine everywhere except for exactly when x is 1. Everything else is getting closer and closer and closer to -1. We can actually say from this graph that the limit of, as x goes to 1, of f of x is -1, even though f of 1 is undefined. I don't know what that function value is. I can't know what that function value is because everything else is going on. So here's the difference in a removable discontinuity and a non-removable discontinuity. Here, what the big focus here, I could plug in one point and everything would be fine. Everything would be connected. Here, this vertical asymptote with things going in opposite directions are really messing things up, and there's nothing I can do over here. But here, I can pretend if I plugged in the point 1, -1, everything would be connected. And we're going to talk about that more in section 2.6. But my emphasis here is, just because f of 1 is undefined doesn't mean that that limit doesn't exist. And here's why. This comes back to this. This comes back to the idea of if I cancel that discontinuity, if I remove this discontinuity. Now I'm going to be the first one to admit that if I plug in 1 here, that gives me 1 minus 4 plus 3 over 1 minus 1. Well, 1 minus 4 plus 3 is 0. That gives me 0. And here's what's special about this. Because this is 0 over 0, when I plug everything in, there's something special that's going on. If I evaluate this and I get 0 over 0, I'm in good shape. And here's the difference. If I plug in -1, I get, let's see, 1 plus 4 minus 3 over 1 minus 1, which is 2 over 0. That's bad. 2 over 0 I can't do anything with, but 0 over 0, something special is going on, and what's going on is that means that there's a point that I can remove, or excuse me, there's a point that's missing, but everything around it is behaving, because what the argument I would like to make is when I do this step to this step, what I'm really saying here is I've got x minus 1 over x minus 1 times x minus 3 over x plus 1. Now, I'm hoping as long as x isn't 1, this value is 1. This is just 1 by itself if x is not 1. So, because this if x is 1, it's 0 over 0. If x is 1, what's happening is this is behaving as 1, and this is what's taking over. And the idea here is, hey, look, this is what allows me to do it. If I can say everywhere else it's 1 except at the point of discontinuity, that limit is going to exist, and I can simply come in and say, let's do it on this side so we can still look at this work. The limit as x goes to 1 of x minus 3 over x plus 1 is the same as the limit as x goes to 1 of f of x. These two things become the same, which means now I can just plug in for 1. So I've got 1 minus 3 over 1 plus 1. Well, that is -2 over 2, which is just -1. And hey, look, that's what we got by graphing. what the argument here is, if I have a special case where I have 0 over 0, when I plug in that value, now we know that we can't divide by 0. 0 over 0 is undefined, but everywhere else that value is going to be exactly the same, and this creates an opportunity for us to simplify things down by canceling and evaluate a simplified rational instead of the original rational. I hope that you have found this video useful. This skill is actually going to be very important as we move into chapter 3. So please make sure you understand the idea of if I create a situation where I've got 0 over 0 and I can eliminate that point, then this limit does exist, which is why we have this gap here, whereas here we have a vertical asymptote. Again, I'm sorry. I hope you found this video useful, and good luck in the coming semester.